Good morning, everybody. All right, so let's take just a couple of minutes and kind of review some of the things that we've learned over the last several weeks. We've learned an awful lot about acids and bases, particularly Lewis acid, Lewis base theory. We've learned about structure. We've learned about formal charge. We've learned about isomers, which is part of structure, obviously. What else have we learned about? What comes to mind? We've learned about spectroscopy. We've learned how we identify functional groups, right? So by definition, we've also learned an awful lot about functional groups. And at this point, we've really learned about what they are, right? Not necessarily what they can do for us. Today, we're going to start talking about what they can do for us, how we can take one functional group and transform it into another functional group. That's the power of what we can do in chemistry. We can take functional groups that we're given, and we can convert them into functional groups that we want. What else have we learned? We've learned about isomers. What else? Started learning an awful lot about nomenclature, right? Y'all are getting to be experts now at hearing a word and thinking about a name, right? At least in terms of simple molecules. If I tell you 2,3-dibromobutane, I'd wager all of you could draw that out, right? And we know that 2,3-dibromobutane can have R, S, right? It could be meso. We've started learning about a lot of words that kind of come into play. And so all of this stuff that we've learned about up to this point has really been preparing you for what we're going to start talking about in Chapter 6, which is chemistry, reactions, converting that one functional group into a new functional group, okay? And so that's what we're going to start with today. We're going to talk about alkyl halides, okay? What is an alkyl halide?
Halogen attached to an alkyl.
Repeat that, please.
Halogen attached to an alkyl.
It is a halogen attached to an alkyl group. For example, right? What would it be fair to say that it's a halogen bound to a carbon? In part. But there are several different alkyl groups. Are what kind of hybridization? sp3. Right? So everything that we're dealing with here is going to be a halogen, fluorine, chlorine, bromine, or iodine, right, attached to an sp3 hybridized carbon of some sort. And these things undergo nucleophilic substitution, okay, where we can take the alkyl halide and we can do a substitution on it and replace the halogen for something else. And that's a really powerful thing. Alkyl halides are very, very useful organic molecules. And so how we make alkyl halides, how we utilize alkyl halides will be very, very important throughout the rest of this course sequence. Okay? So, as we mentioned just a second ago, right, we're going to have some sp3 hybridized carbon atom attached to a halogen. Okay? For our purposes, we exclude astatine, which is at the very bottom, because I think there's only like 3 milligrams of astatine in the entire world, right? I say that. I mean, it's tiny, tiny amount, right? It's not a naturally occurring substance. It's synthetic. And so we're going to be talking about fluorine, chlorine, bromine, and iodine, okay? So, for example, if we have a methyl group attached to a halogen, we would call that a methyl halide, right? We can have a halogen that is attached to a primary carbon. That becomes a primary alkyl halide. We can have a halogen that's attached to a secondary carbon, which makes it a secondary alkyl halide. And we can have a halogen atom attached to a tertiary carbon, which makes it a tertiary alkyl halide. You will need to be able to identify primary, secondary, and tertiary alkyl halides because they don't react the same. A tertiary alkyl halide undergoes one type of substitution, whereas a primary undergoes a very different type of substitution. Secondary alkyl halides can live in both worlds, and they will be your bane. Okay? So there are different reaction types that we're going to learn about. Nucleophilic substitution is just not one reaction mechanism. There's actually a couple of reaction mechanisms that we'll talk about in this chapter. Okay? So, for example, if we look, here's an example of a primary alkyl iodide, right? So the iodine is attached to a primary carbon atom. We know this is a primary carbon atom for two reasons. Number one, it's attached to one and only one other carbon, but it also has two hydrogens, right? So we know that that's going to be a primary carbon for an alkyl halide. Here we have a secondary alkyl bromide, right? This is a cycloalkyl bromide, but that's okay. It doesn't matter. It could be straight chain or not. And here we have an example of a tertiary alkyl halide, in this case a tertiary alkyl chloride. Why do we not have quaternary alkyl halides? Carbon can only form bonds, and a quaternary carbon atom is bound to four other carbon atoms. Can't have it, right? Okay? So these are some examples of the types of alkyl halides that we're going to be dealing an awful lot with. Okay? These types of organohalides, these are not alkyl halides. Why are these not alkyl halides? That's right. The halogen is directly attached to an sp2 hybridized carbon atom. Okay? Now, these are useful molecules. Don't get me wrong. They do have reactivity. We do use them for things. But these are not alkyl halides. This is what's called a vinyl halide. The carbon-carbon double bond is known as a vinyl group. Where have you heard the term vinyl before? Vinyl records, which are becoming more and more popular, right? Again. What else? Screen printing stuff. Okay, you can have things printed on vinyl, that peel and stick kind of stuff. Vinyl seats and vinyl materials in your automobiles, right? Vinyl plastic you probably think about, right? And then this is aryl halide. It's attached to an aromatic ring, right? In this case, a benzene ring. So this would be a some type of aryl halide, if, you know, again, fluorine, chlorine, bromine, or iodine there, okay? These, however, notice they contain, on the right here, they contain alkenes and aromatic groups, but these are alkyl halides. Why are they alkyl halides? This is an sp3 hybridized carbon atom, and a halogen is directly attached to it. It's an alkyl halide. Same thing here, okay? Now, when you have a carbon-carbon double bond, and then you have attached to that carbon-carbon double bond an sp3 hybridized carbon, that carbon that's directly attached to the alkene is called an allylic carbon. Okay, another word. These are allylic halides, and they have different reactivity than, say, a methyl halide, but they are alkyl halides, and they will do very similar chemistry. They're just a little more reactive at it for the most part. And this, notice we have an sp3 hybridized carbon attached to a benzene ring. It's called a benzylic halide. This is called the benzylic carbon. They are sp3 hybridized, okay? The chemistry of all of these things is a little bit different. So, for example, if I took the aryl halide and I opened a bottle of it up here in the classroom right now, let's say aryl bromide, you all wouldn't be able to smell much. After a while of being open, you might get a little whiff of something that smells kind of aromatic, okay? Wouldn't burn your eyes. But if I took benzylic bromide and I opened it up in this room, your eyes would start to water. You would feel like I had probably opened up a bottle of tear gas, okay? And in fact, I pretty much so have, okay? And so in my laboratory, we work with benzylic halides a lot, and you can really tell when people have bad technique because their eyes will start to water, okay? You got to work with them in the hood. You got to change your gloves quite often, and so usually when I get a new graduate student, they start working with it, they'll come out of the lab and their eyes are all watery, and I'm like, oh, you probably had your gloves on and rubbed your eye. That's a bad mistake, right? Something along those lines. So these are useful halides. These are useful but not alkyl halides, and they're useful in other things that we'll learn about later on, okay? Nomenclature. The halogen is just like any other substituent. So all the rules that you have learned up to this point for nomenclature do not change, okay? So for example, if we look at this molecule, the first thing that we do, right, is find the longest parent chain. According to this, 7 carbons are in the longest chain. Is that correct? It is. And so the parent is, it's a heptane parent, right? And so we circle it. And so what are the substituents? We've got a methyl and a chlorine, right? Which actually as a substituent becomes chloro. Okay, so if the atom is chlorine, the substituent becomes chloro. Just like methane becomes methyl, chlorine becomes chloro. So if it's bromine, it would be, if it's iodine, iodo. If it's fluorine, fluoro. That's right. Okay? And so we know what our substituents are. Now what we have to figure out is our numbering, right? And so what's the rule for numbering? We're going to try to pick the lowest number, that first point of branching. And so it turns out that it's this way, 1 through 7, from right to left, right? So we have a chloro group at carbon number 2, and we have a methyl group at carbon number 5. We're going to alphabetize our substituents, just like we learned before, and this becomes 2-chloro-5-methyl-heptane. Is that molecule chiral or achiral? Is it chiral? You think it's chiral? Why do you think it's chiral? Okay. There are certainly 4 different substituents here, right? So we have a hydrogen, a methyl group, a chlorine, and then this alkyl group. What about this one? Is that a chiral center? It is. I've got a methyl group, an ethyl group, this thing, and a hydrogen. 4 different things. I've got 2 chiral centers, right? So must it be chiral? It may or may not. In this case, it will be because the substituents are different. There's no opportunity for a meso compound, okay? So if we have 2 chiral centers, how many possible stereoisomers are there? 4. 2 of them will be enantiomers, and 2 of them will be diastereomers. Absolutely. So just a handful of carbon atoms, a chlorine, and some hydrogens, we have the possibility of 4 different stereoisomers. Okay? And notice none of the stereochemistry was indicated, so we don't know whether carbon number 2 is R or S, nor do we know whether carbon 5 is R or S. We'd have to see that with solid wedges and dashed wedges and all that kind of stuff. But right now we're just interested in the rough nomenclature. So that's okay. When we get to talking about alkyl halides, there are some common names that you need to commit to memory. Okay? So for example, this molecule right here, the common name is tert-butyl iodide. And you will always hear me refer to it as tert-butyl iodide. I'm naming it as if it were almost like a salt, like sodium chloride. Now we've got butyl iodide. We're naming it as if it's a salt. Same kind of nomenclature that you learned about in general chemistry. The problem with that nomenclature, a salt this is not, right? These are all covalently bound together, right? Now, I said this is the common name, tert-butyl, because of the T-butyl group. Okay? How would you name that systematically? What would the systematic name for this be? What's the parent? Propane, right? We've got a propane parent. What are the substituents? Methyl and an iodo, right? So how would we number? 1, 2, 3, right? So this would be what? Does I or M come before each other in the alphabet? E, F, G, H, I. 2 what? 2 iodo. 2 methyl propane. And I ran out of room, sorry. So you can call it 2 iodo 2 methyl propane all you want. That's fine. It's perfectly accurate. I won't count it off on the exam. But chemists don't do that. We like to abbreviate. That starts to get pretty long. This is tert-butyl iodide.
So that's like just the only 2 we need to know.
Nope. There'll be others that you'll learn. This one's not so bad, right? You can call this chloroethane, which would be the systematic name, but you will find that most chemists actually refer to this as ethyl chloride. Again, getting back to that salty kind of nomenclature that you learn about in general chemistry. It kind of bled over into organic a little bit, okay? But it is not a salt, so don't confuse that, okay? So let's do a quick little concepts test. Name those two alkyl halides. The one on the left, certainly a little more simple than the one on the right. So take a minute. Got multiple colors. All right, let's look at the white molecule there on the left. First step. We're going to find the longest carbon chain, which is what? Think it's 9? Okay, so we got a what parent? What are our substituents? We got a bromine and we got 3 methyls, right? And so now we just have to determine whether we're going to number left to right or right to left. Which way do we number? Left to right. And we end up with 6 bromo. 3, 4, 5, trimethyl nonane. Because we are numbering from this direction, 1, 2, 3, 4, 5, 6. Because we come to the first point of branching at carbon number 3 this way here, it's 1, 2, 3, 4. That's why we number from left to right. How about for the yellow molecule? What's the parent? It's a heptane parent, right? I made that one pretty easy for you because it just goes from left to right. No zigs or zags, right? Why are we not naming it as a cyclopropane? It's smaller, right? You have to determine what's longer. Is the ring bigger or is the chain bigger? And 3 is certainly less than, what did we say, 6 or 7? So we got a heptane parent. What are our substituents? We got 2 fluorines, a bromine, and a cyclopropyl, right? Cyclopropyl, right? Because it's -1 hydrogen, right? It's an alkyl group. Remember? It's a substituent. So we have 5 bromo, 4 cyclopropyl, 2, 3 difluoroheptane.
When you name cyclopropyl, do you go by the C or the P?
C. Let's talk about some of the physical properties of alkyl halides. It turns out that alkyl halides have a dipole moment. Carbon being less electronegative than the halogens, right? Fluorine's very electronegative. Chlorine's pretty electronegative. Bromine's fairly electronegative. So we're going to have a dipole in these molecules where the carbon is going to take on a partial positive charge. The halogen is going to take on a partial negative charge. That sigma bond between the 2 atoms, the electrons are spending more time, if you will, around the halogen than they are around the carbon, and you have this polar covalent bond. Okay, and so the dipole is in the direction as shown. Okay, and so this is an example of chloromethane. So we will have van der Waals interactions for sure. All molecules have van der Waals interactions. But here we have the opportunity for dipole-dipole interactions. Is dipole-dipole strong, medium, or weak? It's medium. So how is this going to affect the physical properties? Is it going to affect the melting point, the boiling point, etc.? Absolutely, right? And so we would expect that chloromethane will have a higher boiling point than methane, for example, okay? Because of these dipole-dipole interactions. The drawings that you're seeing here are actually created by that software that I have, that Spartan software that I told you costs a couple $1,000, right? These are called electrostatic potential maps. They show us the dipoles graphically, okay? Areas that are more red have more electrons or more negative charge around them, if you will, and the areas that are more blue are without electrons or electron deficient, if you will. And so you can clearly see in these electrostatic potential maps how the dipoles look other than just seeing an arrow. You kind of get an idea of how big the molecule is, you get an idea of the bond lengths, and you get an idea of how the charge is distributed around the entire molecule. Okay? So let's look at some examples of some physical properties. Okay? Now these physical properties are a little bit exaggerated in this case because the molecular weights of the molecules are not really close. Bromine is a heck of a lot heavier than hydrogen. So there is some of this heaviness stuff that's coming into this that's giving rise to some of these big differences in some of these physical properties. But nonetheless, you can clearly see the difference. So if you look at ethane, ethane is a gas. It comes out of the ground. It's part of natural gas. It comes out of crude oil production. It is quite frequently the flare gas that you're seeing on a refinery or on a platform out in the ocean. Okay, they're burning off this volatile ethane gas because they've stored as much of it as they can. It has a boiling point of negative 89 degrees Celsius. So at all the temperatures that we're used to, ethane is always going to be a gas for us, right? We do not typically operate in environments that are minus 89 degrees Celsius. That's really cold, right? However, ethyl bromide has a boiling point of 39 degrees Celsius. You can go down to my lab right now and there's a liquid bottle of ethyl bromide. You can open it up, you can take a pipette, you can pull it out of a certain volume and you can deliver it, okay? It has an increased boiling point because of these dipole-dipole interactions, okay? Does anybody know what body temperature is in Celsius? 37.5 degrees. So we could supply just under the boiling point for ethyl bromide, okay? In fact, you can evaporate ethyl bromide. You can't boil it, but you can evaporate ethyl bromide quite easily in your hand, okay? It turns out that the boiling points and the melting points increases as the number of carbons increase. That's not terribly surprising, right? So if we look at ethyl chloride versus propyl chloride, we can see very big differences in melting point, very substantial and significant differences in boiling point. What's responsible for that? The surface area is bigger. Very good. Meaning what? More van der Waals interactions. More van der Waals interactions, more attractions, more energy it takes to boil it, right? Boiling points and melting points increase as the size of the halogen increases. Quite easily. As you go down the periodic table, or down the family, okay, for the same number of carbon atoms, so here we've got ethyl chloride versus ethyl bromide. As the halogen increases in its size, so does the melting point and the boiling point. Okay? It turns out that alkyl halides are soluble, in organic solvents. What organic solvents have you used so far in lab? Or have you used any organic solvents yet? May not have. I don't know where you're at in the lab right off the top of my head.
Ethanol.
You used ethanol. Okay? Distilled water is not an organic solvent. It's a solvent, but it's not an organic solvent. But you used ethanol. So these alkyl halides will dissolve in things like ethanol. They will dissolve in other alkyl halides. They will dissolve in hexane. They will dissolve in benzene, toluene, things that we typically use to run organic reactions in. They're very soluble. Alkyl halides, however, are not soluble in water to any appreciable extent. Okay? Now I can take some alkyl halides and I can put them in with water and I can get a small percentage of it to go into water. And if I dump that water down the drain, the city of Hattiesburg comes and complains for the pollution. I mean, they can detect it. But you will always have two layers. Okay? Have you all done the separatory funnel experiment yet where you're, haven't done that yet? That's too bad. Well, we'll get to that. Okay? But you end up with an immiscible mixture. Okay? There are some common alkyl halides that you all already know about and utilize every day. So for example, this is Teflon. Notice the halogen is fluorine. What's Teflon useful for other than cookware? I don't know. Is Teflon used in bulletproof vests? I thought Kevlar. Yeah, Kevlar. Yeah. It is heat resistant. I mean, you can make cookware out of it, right? Your nonstick cookware is quite frequently coated with Teflon. What else do y'all use Teflon for? How about those little stir bars in your reactions that you did in general chemistry and stuff, or you're going to do in organic? Those stir bars have to hold up to a lot of stuff. Teflon turns out to be pretty inert. It doesn't hardly dissolve in anything. Okay? That's not to say you can't dissolve it. That's not to say you can't do things with it. You can. But it's overall fairly inert. Okay? Polyvinyl chloride, PVC, right? Sewer pipes, water pipes. This is what you all think of when you think of vinyl. Polyvinyl chloride. Okay? Notice you've got halogen, or the halogens are chlorines, and they're not on every carbon like it is for Teflon, right? But polyvinyl chloride makes nice pipes and things. CFC11, also known as Freon 11. CFCl3, Freon 11. What's Freon useful for? Air conditioning. Freon 11 I do not believe is used any longer. It's been banned. Okay? A lot of these fluorocarbons have been banned because they generate persistent radicals that live up in the atmosphere and destroy the ozone layer. Okay? But if you find some old refrigerants, you can find things like CFC11. How would you name this systematically? I mean, Freon 11, how do you know it's Freon 11? Where does the 11 come from? I don't know. You know? But how would you name that? Chlorotrifluoro? Do we have to put numbers on there? What comes first, F or C? C. So it would be trichloro, fluoro, what's the parent? Methane. That's right. It is trichlorofluoromethane. Now, can you imagine having somebody come to your house and say, I need to replace your trichlorofluoromethane and your... They don't do that. They say, I need to put some Freon in your air conditioner, right? And if it was an old-timey air conditioner, it might have been C11 or Freon 11. DDT is also an alkyl halide. All right, there's the alkyl sp3 hybridized carbon. It's got 3 chlorines. It also has aryl halides, in this case aryl chlorides as well. What was DDT useful for? It's a very potent mosquito killing agent, right? DDT probably did more good for the eradication of mosquito-borne diseases back in the 60s and 70s than just about anything did. But it had a drawback. What was it? Does anybody know? Eagles. It damaged their shells. And the shells weakened them somehow. I don't know how.
Yeah, it like made them super thin.
Yeah.
They cracked.
And they wouldn't hatch. They would die. That's right. And so, however, you can go back many, many years now and look at the literature on DDT, and they were selling this as if this was an environmentally friendly, non-toxic stuff for humans. And as best they knew at the time, it was. There is actually a photograph that I've seen, I can't remember where it was at, of one of the workers at a DDT factory taking a spoonful of it and eating it to prove that it was not harmful. Okay. Huh? As far as I know, he lived. Okay? But, you know, as time went on, as it built up in the environment, they started to notice that there were these problems with the bald eagle population, and they traced it back to DDT. It's a pretty interesting environmental kind of forensic story, a forensic case, if you're interested in that kind of stuff. Go back and study it. Okay? There are other interesting alkyl halides. Chloromethane, for example. This is not only a synthetic man-made thing, but it's also found in nature. Giant kelp and algae make this. Why, I don't know. And it's also part of the emission of Hawaii's Kilauea volcano. So you can go there with a detector. You can detect chloromethane emissions from this particular volcano. You can also detect it around areas where there are giant kelp. Okay? Chloromethane is also a carcinogen. So volcanoes are emitting these carcinogens, as are these giant kelp. Dichloromethane, which is a common, or which is the correct name, 2 chlorines, dichloromethane, but you will quite frequently hear me and others refer to it as methylene chloride. That's another common name. Where do we get the term methylene? It's because of the CH2. Every time you have a CH2 group in a molecule, those are methylene units. Okay? And so methylene, CH2, and then the chloride. Okay? This is an important solvent. My lab uses methylene chloride like it's going out of style. For those of you in polymer science, you will use methylene chloride an awful lot. Okay? Methylene chloride used to be utilized quite a bit in the decaffeination of coffee. So coffee beans would come through, they would kind of crunch them up a little bit. They would pass through some machine that they had methylene chloride through it. Caffeine is highly soluble in methylene chloride, and so you can remove the caffeine quite easily. The problem is methylene chloride, not particularly health friendly. Okay, does anybody know how they prefer to decaffeinate coffee these days? Some coffee is still decaffeinated using methylene chloride, but today the vast majority of producers like to utilize what's known as supercritical carbon dioxide to decaffeinate coffee. So you can put a lot of pressure on carbon dioxide, it will become this supercritical fluid, and for whatever reason, I'm not an expert on supercritical fluid chemistry, but caffeine becomes highly soluble in supercritical carbon dioxide. You then separate that out from the coffee beans, you release the pressure, the carbon dioxide gets recycled, and the caffeine sits in the bottom of a flask. Carbon dioxide, if you ingest it, does not kill you, right? It does not cause cancer, right? So, that's good. Halothane, okay? Notice all these halogens on this thing. This is a general anesthetic. This is what knocks you out, okay? Does anybody know what they used to use early on as an anesthetic? Diethyl ether. So you would breathe ether vapors and you would conk out and they would do their surgery. The problem with that is if you're having heart surgery, for example, they have to stop your heart, right? And then they have to restart your heart. How do they restart your heart? They zap you with electricity. What happens when you zap something with electricity? What do you typically get? You get sparks. And what happens with ether around sparks? Boom. And people's chests have caught on fire from that. I mean, there are examples of that in the literature. Halothane, however, is non-flammable. So they can do the surgery that they need to do. Okay? We have talked a lot about the fact that we can have different halogens. What are these electrostatic potential maps telling us? as we go from methyl fluoride, methyl chloride, methyl bromide, methyl iodide. What can you see from those electrostatic potential maps? Pardon? It looks like we're getting a little more polar. In what way?
There's a higher electronegativity difference.
In which direction?
To the right, or the direction of the halide.
Okay, so as we go down the family, right, is this as red as this?
Actually,
It's not, right? So the polarity depends on the difference in electronegativity. So it turns out that fluoromethane is actually quite polar compared to iodomethane, right? But what can you tell me about the bond lengths? What can you see there? They're getting longer. So is a longer bond stronger or weaker? So which one of those do you think is more reactive? The weaker one, the iodo. As we go down the family, the reactivity increases. Okay, and so the electrostatic potential map is showing us those bond lengths aren't the same. When we draw it on a piece of paper, you will draw C-F, C-I, and you'll make that dash about the same length out of convenience. But in reality, the bond lengths are not the same. Okay, and so the carbon-iodine bond is longer. It is more reactive than the carbon-fluorine bond. And that makes some sense. Okay, as we have a bigger atom, the bond length should get a little bit longer, right, as we're measuring it. Okay. Also, we know that carbon-fluorine bonds aren't particularly reactive because we use Teflon all the time. You wouldn't want to use a nonstick coating that's highly reactive. It wouldn't last very long. It'd contaminate your food. It would do all kinds of chemistry. It would probably stink up the house. None of which happens with Teflon. Okay, you will not have a polymer with a bunch of carbon-iodine bonds that you put on your cookware. Okay. So now we're going to start talking about some real chemistry. We're going to talk about how we take a functional group and convert it into another functional group. So how do we convert a halide into another functional group? Well, we can use what's known as substitution reactions. So here we have an alkyl halide that's just generically represented with an X. So for right now, assume it can be any halogen. We'll learn about the reactivity of the halogens better later. Here we have a nucleophile. Okay? That nucleophile has a lone pair of electrons. And that nucleophile can displace the halogen. So now we have a carbon nucleophile bond, whatever that nucleophile happens to be, and we have the halogen leaving as a halide. The halogens in alkyl halides, the halide is what we call the leaving group. It leaves, and the nucleophile replaces it. Okay? And there are a couple of mechanisms that we'll learn about. Okay? Notice that the nucleophile has a lone pair of electrons. Therefore, it must be a Lewis what? If it has a lone pair of electrons, it's a Lewis base. So that means that alkyl halides must be what? Lewis acids. That is right. They behave as Lewis acids. Now, wait a second. Did you all ever think of an alkyl halide in general chemistry as being an acid? No, but Lewis theory allows us to look at the electrons. If it's an electron pair acceptor, it's an acid. If it's an electron pair donor, it's a base, right? And so you can also have reactions where alkyl halides will react with a base and eliminate something to give a new carbon-carbon double bond, and we'll learn about that as well. These are the two general types of reactions that alkyl halides undergo. They can undergo nucleophilic substitutions, and they can undergo elimination reactions. Okay? And with this slide, I'm going to tell you something very important you need to commit to memory. All nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles. Okay? All nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles. A nucleophile reacts with a carbon, which is what's happening here. A base abstracts a hydrogen. It doesn't react with the carbon. We've not changed the bonding between these two carbons. They're still bound together. Yes, we've changed it in the sense that now there's a double bond, but we haven't, the nucleophile has not attached itself to a carbon. Okay, so here the base removes HX, if you will, and you end up with a new alkene. So repeat that rule for me. Very good. And we will learn how to determine whether or not something is going to behave as a nucleophile or a base. I am not going to give you a big, huge list right now and just tell you to memorize it. You need to go through this and learn why certain things behave as bases and why certain things behave as nucleophiles through experience. It's the only way that you'll be able to commit it to memory accurately. Okay? So let's look at a couple of real reactions. Here we have chloromethane. We're going to react it with hydroxide from sodium hydroxide. Okay? And we make methanol. Okay? So what's my functional group transformation? I'm going from a what? I'm going from an alkyl chloride to an alcohol. We can do that all day. I can take alkyl halides and I can convert them into alcohols. I can take chloroethane and I can turn it into gin. Okay? Be an expensive way to make gin, but I can do it. Okay? We can make alcohols from alkyl halides. I can also take an alkyl halide and react it with a sulfur nucleophile. Okay? Looks very similar to hydroxide, except this one stinks. Sulfur always stinks. And I can go from an alkyl halide to what? Is that a sulfide? It's a thiol. Yeah, sulfide is where we have the sulfur connected to two carbons, right? So I can also take alkyl halides and I can make thiols. I can take alkyl halides and I can react them with what's called methoxide, which is nothing more than an organic derivative of methanol. Okay? It's negatively charged. It's a good nucleophile. And I can make what? What's that functional group? That's an ether. You just learned 3 reactions. Alkyl halides to alcohols, alkyl halides to thiols, alkyl halides to ethers. Okay? One of the things that you're going to want to start doing right now is building what I call road maps, where you put a functional group in the middle and you start going out from that and writing out the chemistry that it can undergo. I highly recommend that you do this on an 8.5 by 11 piece of paper so you can add to it. Don't use a note card. But what I would do is put an alkyl halide in the middle. I would put some more information, like X can be chlorine, bromine, or iodine, for example. And then I would draw out, going out from it, things that I can do. So I can make alcohols if I react it with hydroxide. I can make thiols if I react it with something like that, so on and so forth. The nice thing about this study method is when you're at home watching television and a commercial comes on, you can pull these out and you can quickly study for about 3 or 4 minutes, put them away. But you're going to need to know what you can transform. You need to know that alkyl halides can be converted into alcohols, into thiols, into ethers. And we'll be adding to this list as we go on. Okay? You need to be able to know that by sight. And the only way you're going to have that information is if you practice it. Okay, not just with your homework, but all the time. And one of the quickest ways to do it is to utilize that wasted time that you have during the day. Waiting on the elevator. You could pull this out, right? The elevator takes 4 or 5 minutes. So pull out the thing, study a few things. Okay? Not a problem. Okay? So notice the balance in this reaction. So on the left, we have an alkyl bromide. What's the name of that? How would you name that? I can't just name it propyl bromide. Why not? I could get away with ethyl bromide because no matter where I put the bromine on ethyl bromide, it's always carbon number 1. Is that the case here? No, I can have one bromopropane, and I can also have 2 bromopropane. So it matters. So this is 1 bromopropane, right? 1 bromopropane reacts with sodium hydroxide, which is going to be the nucleophile, and we end up with 1 propanol, an alcohol, plus we end up with sodium bromide as a salt that falls out of solution. Notice the nucleophile, we are using what kind of arrow? Because I'm moving a pair. And that pair of electrons is attacking, organic chemistry can be violent, okay? It is attacking this carbon, okay? The nucleophile attacks the carbon. I can only have 4 bonds to that carbon, so what has to happen? The bromine has to leave. So as the nucleophile is attacking the carbon, the leaving group is leaving, okay? And so this arrow is telling me I'm forming a bond between this oxygen atom and this carbon atom, and the halogen is leaving. Now, organic chemists quite frequently ignore the salts and all the spectator ions because we're not interested in them, okay? So keep that in mind. You'll quite frequently see me write this and hydroxide and the alcohol product, okay? So here's another example. Here we have a nitrogen atom, okay? What kind of amine is this? Is it primary, secondary, or tertiary? It is a tertiary amine. It will react with an alkyl halide. Again, the nucleophile attacks, the leaving group leaves. I end up with a positively charged thing called a quaternary ammonium salt. Oh, wait, there's another reaction. Look at that. I can make quaternary ammonium salts. Very useful reaction for making antibacterial hand soaps. Almost all of them contain quat salts, as they call them. They're antibacterial in nature, okay? So we are at the end today. We will finish this stuff on Monday and then continue on into our stuff. I need you to turn in your inverted lecture and your bonus note card for the thing that I assigned you on Wednesday. You can just leave them up here at the top. Please separate them out. Have a great weekend.